everyone. We're continuing on with the acids, organic acids, amines, and acid derivative properties. And so in this lesson, we're going to look at some of the reactions of organic acids and amines, and in the next one, we'll look at some more. So first of all, there are three reactions that involve amines. One we've already seen right near the beginning. We saw a way of forming an amine. So this is one of the nice things about organic chemistry. We see some of the same reactions again. So you've already learned this one. When we learned it, I said, oh, we'll learn about those later. And we're finally there learning about what is formed when ammonia in ethanol, not in water, is substituted into an haloalkane. And I know on best choice, I think, it might say concentrated ammonia instead of ammonia dissolved in ethanol. That works as well, so not much water. But the interesting thing here is that the nitrogen has three places where it can substitute with the chlorine. It has three hydrogens around it that can be substituted, so we get a mixture of the products. So then the ammonia itself can join with one of the carbons that used to be part of the haloalkane, or two carbons or three carbons around it. So we can get a primary amine, a secondary amine, or a tertiary amine. Don't think I remembered to say this earlier. So we saw these words primary, secondary, tertiary with alcohols and haloalkanes. It's the same word, although this time it's the nitrogen that we need to look at. And how many carbons is the nitrogen bonded to? With the other two, with haloalkanes and alcohols, they can only bond to one carbon. So we had to look at the carbon that it was bonded to and how many carbons was that carbon bonded to. But this time it's the nitrogen directly. So it's a little bit different, although the idea is still very, very similar. The second one, I guess, is something that you also already know because we've done so many acid-base reactions, but this is an important reaction of amines. They are bases, and so they can react with acids. So it's just like a normal acid-base reaction, and is what makes a base a base. It can accept a hydrogen. What makes an acid an acid? It can give a hydrogen. It can donate a hydrogen. There is an interesting thing about this, though, and here I've written it all in solution, aqueous, aqueous, aqueous. So if it were all in solution, we wouldn't really see it unless we had an indicator or something. We could use like litmus paper also to identify an amine. But if everything were in the gas phase, and all of these can become gases very easily, and if it were all done in the gas phase, then we would actually see something. Because when it produces the two ions, they're not dissolved in water, and so it's an ionic substance, and so that is a solid. And a solid forming in a gas phase, that looks like white smoke. Well, this would be white because it is white, but it looks like smoke, solid forming in the air. So we could actually see that reaction happening. So that could be useful as an identifying reaction. And the third one, I've used up a bit more space than I planned on here, but that's okay. The third one are condensation reactions. But we'll see this later because that's one of the main reactions of both acids and acid chlorides. So I'll wait until we discuss those where we see them. So that's the amine reactions, that's it. So what about carboxylic acids? Well, the main ones here are, well, the main one, the one we'll spend the most time talking about, is the condensation reaction. But also carboxylic acids can undergo substitution. So we've seen this so much before, and this is actually a link with one of the acid derivatives. It's forming an acid chloride. And there are three possible reagents, and I saw this briefly with alcohols. These strong chlorinating agents can substitute a chlorine onto an alcohol as well, and they're so strong they also work with acids. It's a very simple substitution reaction where there was an OH group on the acid as part of the acid group, and it just substitutes and becomes an acid chloride. There's a chlorine instead of an OH and still a C double bond O. There, I've just redrawn them out, kind of expanded, showing all the bonds. So that C double bond O stays the same and the OH is replaced with a Cl. So this is important. This is how we get an acid chloride, and we'll see acid chlorides can be useful to use to make other products as well. I haven't written acid-base reactions here, although they do that. It is an important one. But the main one, the main organic reaction that carboxylic acids can do is condensation. So the first one, we could call it specifically esterification, making an ester, and it's where the carboxylic acid joins with an alcohol. That's what a condensation reaction is. And it does need a reagent as a catalyst, and we usually warm it a bit. It doesn't have to be too hot. Just like in a warm water bath, so sometimes we won't even write the heat, but it is heated a little bit. You can write that. So let's look at an example. What is this condensation reaction? So in a condensation, always the part of the molecules are lost, and in this case it's the OH from the acid and the H from the alcohol, so that makes water. So water is lost. And that allows a new bond to form between this carbon and this oxygen. So I'll normally flip the alcohol over the other way to make it fit more easily. Sorry, there was a little typo there. I'm lucky. I'm glad I saw that. So this is now here, and I've just flipped it over in my mind and written it from left to right, or from right to left, the other way. And that is now an ester. This is how esters are formed. And yeah, this is a classic example of a condensation reaction. There's always a small molecule that's lost. With carboxylic acids, it's always water that is lost to make room for the new bond so they can join together. So you might be thinking, oh, what else can the carboxylic acid do in a condensation reaction? It's possible to make an amide with an amine by joining with an amine, or ammonia as well. However, I'm not going to give you an example of this because it is very difficult to actually do this reaction. So without special conditions, very high temperature, very concentrated acid, then condensation reaction does not happen. Just a simple, normal acid-base reaction would happen if we did it just like in the lab in school. So it's good to know that. And sometimes we'll ask you this: what reaction will happen instead if we tried to do a condensation reaction between a carboxylic acid and an amine? It won't do that. What will it do instead? It will do a normal acid-base reaction. I might as well finish this page. So on the bottom here we've got forming an ester. This is quite an interesting thing. Unfortunately for most of you, you're not in school, so I can't share with you some of the esters we have here and let you actually smell them in real life. But a lot of these smells you know. Esters smell fruity, usually fruity. So I know you all know the smell of banana. Well, probably most of you know the smell of banana. Most of that smell, it's a mixture, but most of that smell is from an ester. Almond smell, strawberry smell, all of these, at least part of them, come from esters. There are also some esters that smell like glue or solvent or paint, and we have one of those as an example here. So it's not always, that's why we have to say usually. But usually they have a fruity or flowery or pleasant smell, usually. Mint Some of the minty smells are also due to esters. And while I'm thinking about it, I normally mention smells of other things. So we said how acids taste. They also smell sour. No, vinegar. Think of vinegar or even think of oranges. When you smell an orange, it's kind of a sour smell, similar like the flavor. Many of you will know the smell of alcohol, especially after 2020. We've been sterilizing our hands a lot with alcohol. And astringent is a word for that, but even if you just said like alcohol, people will know what you mean. And most alcohols smell similar. Okay, but that's what that alcohol smell is, can be described as astringent, kind of a strong smell, not really pleasant, not really fruity, but strong. Again, it's too bad we don't have you here so I can make you smell some of these things. But amines smell, their structure is a bit like ammonia, and their smell is a bit like ammonia. And many of the smells we know, many of the fish smells, especially strong fish smell, like kind of old fish smell, is caused by amines, by having the fish protein gives off amines as it gets older. And other ones like aldehydes and ketones and things, they're a bit all over the place. Some aldehydes also smell fruity, but some of them smell really sour or really astringent. So that's why I'm not going to say anything about them here because they're kind of hard to predict what their smell might be like. But smell, because our noses are organic and these molecules are organic, that's what our noses are designed to do, to sense organic molecules and structures. So they're quite amazing. And this is quite an interesting biochemical link again. We are these kind of molecules. So yeah, that's one reason I really love this unit. So we'll carry on next time, finish off the rest of the properties of this family of compounds, and I look forward to seeing you. Bye-bye.